Hello everyone, this is Spencer from Hydromantis, and thank you for joining our webinar today. This is the last one that we're doing for 2015. And today we're going to be talking about process control, and specifically how we go about modeling controllers for controlling nitrification. And so since we have a large suite of different types of controllers that can be used, my plan for today is to run through relatively quickly how we set those up, how they're implemented in your particular layout, and then let's run some simulations and compare a few things against each other. So my name is Spencer Snolling. I'm VP of Product Development here at Hydromantis, and I'm glad that you could join us today. So as I mentioned, I'm going to very briefly discuss how the controllers work in GPSX. So I'm going to assume that you're already kind of familiar with the software and that you know how to set up a wastewater treatment plant. We're going to be working with a conventional activated sludge plant today that does nitrification. I'm going to talk about the different types of controllers that we can have for DO control, for dissolved oxygen control, and then also talk about how we can have direct ammonia control options as well. So in order to do that, I'll have some slides that I'm going to explain a few things, and then we're going to run some desktop demonstrations of all of those different types of options. And while I was setting all of this up for the webinar this week, I found that some really interesting results there. So I made a nice little table of how everything will kind of turn out, and we'll highlight that as we go along. And as we always do in our interactive webinars that we have here, there's always the opportunity to field questions, and I will stay at the end of the webinar to answer any questions that you might have. So if you have your GoToWebinar dashboard open, there should be a questions panel that is available to you. So feel free to go ahead and type the questions in as they come up to you as we go along. I usually like to save them and sort of answer them all together at the end. Okay, so let's jump right in. So there are a number of different types of controller options that are available for you to attach to your model in GPSX. And these have all been there for actually many, many releases of the software. So all the PID control loops and the timing controllers and so on, those have all been there pretty much since the very beginning. So many of those very common control loops that you may want to take advantage of, such as a DO controller, are already sort of built in by default into the unit process objects. So if you're a GPSX user, you've probably already built a layout where you turned on a DO controller by selecting it from the menu. In the background, we've actually got the PID loop control code already written in place for you. You don't have to do anything extra other than just turn it on and set the DO set point. We've already got all the tuning in place and all of that. However, we also have a number of these pre-configured types of controllers that are sort of generic. You can grab them and put them on your layout, and you can hook them up between any particular control variable that you want to be able to control and a manipulated variable. And they're completely open-ended. You can do anything that you like with them. So the ones that are built in are present in most of the aerated type objects, such as the CSTR and the plug flow tank and so on, and all of the pump connection points. So in GPSX, you'll notice there's a pump symbol on the object wherever there's a connection point that allows you to specify a pump flow directly. And in almost all of those cases, that pump can be controlled with a PID control loop. And you'll note here, if I open up just a regular controller or regular pump flow menu, you'll see that that controller can be turned on with this on-off button, and that you can set that control variable there. And if you click on this More button, that is going to open up the second panel that you need to specify a few things here. Specifically, what is the control variable that I'm trying to set? And you have to actually go and find the cryptic variable name of the variable that you're trying to control in GPSX. And that's pretty easy. You can just hold your cursor over one of the variable names in the menus, and it'll pop up, and you can enter that here. Now, I won't go into a lot of that detail because we actually did a whole separate webinar on that last year where I spent a good half hour on that, and it's actually part of our regular training package, and you can see that in our videos on our website. The other thing you have to do is set up the tuning here. You have to specify how the controller reacts, whether it goes with or against the direction of the manipulated variable, and you have to specify things like gain and integral time and so on, and the sampling interval. That allows you to basically set up any type of controller that you want between any two variables in GPSX. So that's the ones that are already built in. Now you can also do these customizable ones. And as I mentioned earlier, these have been in GPSX for a long time. Now I'll make a really quick detour here by mentioning that you're probably used to seeing them in version 6.4 and previous to that for many years, finding our generic controllers in the toolbox object. So if you right-click there and you go to the models menu, you'll see that we have, PID forward and PID controllers and on-off controllers and so on. Those are all where we used to store them. Now, we found that this was starting to get a little bit overclogged with models, so we actually changed it so that in the new version of GPSX that's coming to you shortly, in version 6.5 and onwards, the regular controllers that you may want to take advantage of are actually in their own objects. You can just plunk them down on the screen, as many as you need, and you'll be able to quite clearly see which kind of controller that you're using, whether it's a PID where you can see on the screen here that looks like a control variable coming into line with the set point, or it can be a timer, or it can be an on-off controller. This allows us to sort of see things a little more clearly and to make things a little easier to use in the newer version of GPSX that's coming along shortly, and these are all found in a process control panel that's brand new starting next version. So I'm going to show you in the demonstrations that I'm running today in version 6.5, so you'll be seeing those objects there. So there are several different ways that you can dynamically control for nitrification in your plant to be able to control the ammonia in that effluent. Now, most of them are based around the idea that you are going to adjust the aeration in some way or another to meet that oxygen demand in order to do that nitrification. And you want to be able to do that dynamically. So as that demand changes during the day, as the loading changes or the temperature changes or configuration, the way that your plant is being run changes during the day, you want to have a controller that can, respond to that. So the different types of controllers that I'm going to show you, they differ in what the controller is monitoring and also how it's going to implement that change in that manipulated variable. So there's basically two different kinds that you can do. There's DO control, so that's changing the airflow to your activated sludge tank in order to meet the specific oxygen concentration that you set. So I want to have a DO set point at 2 milligrams per liter, and so the controller adjusts the airflow in some way or another to be able to meet the requirement, and it monitors what the DO is doing. The other one is ammonia control. So rather than having the controller look at the dissolved oxygen, it is actually looking at the effluent ammonia, and it's making changes to the airflow based on what it's seeing there. And that's a different kind of thing, and it behaves a little differently. But both of these things can be modeled in a couple of different ways each in GPSX for a conventional activated sludge plant. Okay, so I'm going to get on with some simulations right now, and as I'm doing that, I'll explain 4 different ways that we can do those types of controllers. Now, first of all, before we get started, because I'm going to be running the same plant with the same dynamic influent, I just quickly will describe it for you here. This is the plant that we're doing our control experiment on. It's a 50 NGD plant, and it's got a dynamic influent that's coming in. We're also running it, in order to make things challenging, we're running it relatively highly loaded and also at a cold temperature. It's at 10 degrees Celsius. And we're also going to make the influent change quite a bit while the simulation is running. And we're going to do 15 days in order to see what's happening. So the influent comes in. There's some primary clarifiers there. There's conventional plug flow activated sludge tank, and this is using diffused air. And then we have a secondary clarifier with the recycle, and then all of the concentrations of ammonia that we want to control are coming out here at the back end in the effluent. So pretty standard type of model that we would use. So as I mentioned, the amount of ammonia coming into the plant is quite dynamic. And in fact, we're changing not only the ammonia, as I'm showing it here, but also the COD and the phosphorus and the flow rate. So there's quite a lot going on in this plant. Now this, as you're looking at it right now, here's 15 days of influent ammonia concentration. You can see it moves around a lot. I realize this is not actually very typical for what you would see in a municipal wastewater treatment plant. However, for the purposes of today's webinar, I wanted to do something that had a lot of swing to it, that had a lot of dynamics in it so that we can really investigate what these controllers are going to do and how they're going to differ from each other. So we gave it a particularly challenging thing. And I wanted to make sure that it had at least a couple of good spikes in there in order for the controller to try and do something to handle that spike, and so we can see it. So when we start running some simulations, you'll see how it responds to that. Okay, so the first thing I'll do is, before we get any controllers on, I'll show you what it looks like when we run it with no control at all. So our first simulation here for this particular plant, and I'll just quickly show you what this plant looks like here. As I mentioned, we're working with this regular conventional plug flow activated sludge, and we're going to run a steady state simulation first, followed by 15 days of dynamics. And we can see here, if we're looking at the panel up here at the top, that we're reading in data from an Excel spreadsheet that will allow us for the changes to take place over these 15 simulated days. So you can see here that first of all, the DO, which is in red, is changing over time, and you can see that the effluent ammonia is also changing over time as well. So here's the actual airflow rate, and in fact what I'll do is, I've got it shown a little bit better on a slide here. The DO is in red, and of course it goes up and down as the loading changes to the plant. And this is because our airflow, shown in blue, is a constant. We don't have any controllers turned on at this point. So the DO ranges between sort of 6 and 7 getting up here, and then it gets way down to about 1.5, and it goes up and down. I tried to set that airflow rate, so basically it didn't go below 2 milligrams per liter too often, so that we could get you know, a reasonable amount of consistent treatment, consistent nitrification in this plant. So it's running at about 2,200 milligrams per liter of mixed liquor and 6-ish kind of 6 days or so of SRT. So that's what it looks like. That's what the behavior is. Clearly, there's a lot of dynamics going on, and you can see that the DO goes up and down quite a bit. So this is what the effluent looks like. We have really great treatment, fully nitrifying, and then there's a period where it's really challenging because there's fluctuations in the flow and fluctuations in the loading, and then it goes back to a period where it's not so challenging, and our DO goes back to, pardon me, our effluent ammonia goes back to 0.1 or whatever, and then there's a little spike at the end. So this is sort of the thing that we're going to compare all of our controllers against. And what I'm going to do is I'm going to keep track of the amount of effluent that is, pardon me, the amount of ammonia that comes out in that effluent over the 15 days. So what I've done is actually I have integrated underneath this line here the flow times the concentration so that we have a mass flow, and then I integrated that over time, and this tells me that there were 9.7 tons of ammonia that came out at the back end of this plant over those 15 days. Excuse me. So that's our starting point, and we're going to see what we can improve upon by going to several different types of DO controllers. Okay, so what we're going to do is, very first one, straightforward, simple, PID dissolved oxygen control. And so what's happening here is we have our regular bioreactor, and this is the supply of air for the diffused air system. And we have a PID controller and some sort of a probe here to give us a signal about what the DO is at any time. And that controller then activates a valve or a drive or something that controls the amount of air that's coming into that reactor. And by looking at what the DO concentration is, it can make changes to the amount of air that's being supplied. So traditional PID control, and it does this on a consistent basis, making large or small increments, and it does this every 5 minutes or whatever you've specified in your model. Okay, so I'll just show you how you set one of those up very quickly here. So let's get rid of this layout and go on to the next one. Now, as I mentioned earlier, we already have PID controllers built into this activated sludge tank already for you. But if you wanted to do it explicitly on your own, just so that you got the full feeling of designing a controller with airflow and so on, you put down one of these controllers. They're found in the process control panel. And we have to specify two things. One of them is the control variable. You turn the controller on, and you have to specify what the DO set point, pardon me, what the set point for your particular control variable is. In this case, we're controlling dissolved oxygen to 2 milligrams per liter. And then we have to go in and fill in some of that other information, as I mentioned earlier, the name of the variable, how frequently the controller takes an action, and the tuning and so on. So you can see all of those values I've entered there. The other thing you have to do is specify the manipulated variable. This is the thing that is going to be adjusted. So in this case, we're looking at airflow here. This is the cryptic variable name for the airflow in this particular tank. And we can see that we are going to say that it can go between 1 and this is actually in units of meters cubed per day. And there's a minimum and a maximum in the starting point for this to be able to go from. All right, so that's been set up. And so we can run a simulation here. And in this particular case now, again, I've kept the same colors that we can look at. The blue is the airflow. Now, instead of being a flat line like it was last time, it is responding, because it's being controlled by the controller, in order to have our DO, which is in red, match up to our DO set point, which is in black. And again, what I'll do is I'll pop back to my slides here because they're a little bigger and you can see a little better. So the red kind of hidden here a little bit, but you can see it bounces around, but essentially that controller is doing a good job of keeping the DO very close to the set point, even though things were fluctuating around and our demand was going up and down and the amount of air being supplied was going up and down. And this is the airflow as it was required in order to meet this DO set point as we moved along. Now, if we want to compare that to what we had last time, this is where the where the airflow was set last time. And we can see some of the time it's below the amount. That was when the demand was low. Some of the time during this peak here and the other peak at the end, it had to increase the airflow quite a bit in order to meet that demand. But as you can see, it's working as it wants to, and it's doing the job. And you know, on average here, it's spending less time, spending more time below the constant amount that we were using in the previous example, and less time above it. So in other words, we're spending a little bit less energy here to be able to do that. Okay, so what does that get us? Now, if I go back and I grab the numbers out of there, how much ammonia went out in that effluent? It's a comparable amount in this particular case, but we're using a lot less energy. So I just opened up the operating, the operating cost menu and plotted all of the details about the aeration. That is part of standard of GPSX. We calculate the energy requirements and what the cost is associated with that. And I got this number here, 63,000. So quite a bit of savings. Basically, you get the same effluent. Okay, moving on to number 3, an on-off DO controller. So same kind of thing, except instead of doing gradual adjustments like a PID controller would, this is either all on or all off. And actually, it's a little bit misnamed. It doesn't actually have to be completely off. It's just basically a high, low, and there's 2 settings. So you have your controller, and you can see here now the symbol showing clearly that there's an upper bound and a lower bound, and you're trying to keep your control variable between those. It's looking at the DO in the tank, and it is making changes. But this one, it clearly just has an upper setting and a lower setting. So let's quickly look at that. Oops, I need to stop the simulation here. Move on to 2A. And let's take a look at that one. Again, you have to specify your control variable. This is the thing that we want to be able to control. Oxygen in the tank, and we have a high limit and a low limit. We don't want it to go above 4. We don't also want it to go less than 1. And we're going to make an action here every 15 minutes. And the thing that we are manipulating, of course, is the airflow, just like we were the previous time. We have the same limits here. So, again, let's run that one. Now, I had to split this up because there's a lot of stuff going on in these graphs here because the controller is activating on and off and on and off, and it bounces back and forth quite a bit. So I've separated out these graphs here a little bit. You can see basically that this airflow is just consistently going up and down and up and down and up and down. And then when it hits this point where we have that ammonia spike, it's actually just keeping it at the maximum the whole time because it's doing the best job it can. So once again, back to the slides because they're a little easier to see here. We can see that it was basically fluctuating back and forth very rapidly between the upper and lower. And then we had a period of time where it wasn't able to actually even ever get above the upper limit. So it just kept the airflow at the high amount. And then there was fluctuating periods. So it's not a great controller in this particular sense. DO actually, of course, reacts very quickly to changes to the airflow. And for that reason, an on-off controller isn't really necessarily the best type of control to do, because it's going to bounce back and forth between the two settings. If you try to control it to a tighter band, it's going to make more changes and so on. So anyway, but just for comparison's sake, let's take a look at that. That gave us 14.5 tons of nitrogen in the effluent, pardon me, of ammonia in the effluent, and a comparable amount of energy spent to that PID controller. So same amount of energy, but it didn't really do as good a job as controlling the nitrification. Okay, moving on now to the ammonia controllers. So now we're no longer looking at the DO concentration in the tank in isolation, knowing that that will help to do the nitrification. This is looking directly at the actual effluent ammonia. So we're going to start with an on-off controller, and we can see here this controller is now connected to, and it's taking its sample from the effluent of the clarifier, but it is still making its changes to the amount of aeration that's happening. So now it's an on-off controller, meaning that we have that upper and lower bounds again. So let me pop over to that example. Okay, so we can see here that this ammonia on-off controller here is at the end. And if I go to the control variable now, instead of seeing the variable here that was previously for the dissolved oxygen concentration in the aeration basin, this is now the ammonia concentration in the effluent. And again, we can have an upper and lower bound and a sampling time and so on. And we are still controlling the airflow. So these settings are the same as what we had previously. So now we're doing on-off control directly from looking at the effluent ammonia. Okay, so let's just quickly take a look at what that looks like. Now, as I'm sure you would be aware, the rate at which the effluent ammonia changes is much slower than the rate at which the DO would change. So this is a much more gradual controller, and we can see here that when the ammonia in green hit that upper limit, suddenly it pushed up to the top amount of air that it can have. And then when it comes back down again, eventually it will drop down again. Right at the very beginning here, since it was very low, it was using the lower aeration set point. And it's a little bit more crude type of control, because you are essentially looking at something that's reacting slowly while you're making your changes one way or another. So, however, it does what it's supposed to do, and you can play around with the settings of what are the appropriate high and low settings and what are the appropriate airflows to be using at those. And let's take an analysis here of how we did. So essentially, when this thing runs out to the end, we can see I set a reasonably tight bound here on this in order to sort of make it similar in approach to what we were doing earlier. And you can see that the in blue here, the airflow, it spends some time at the lower limit and at the upper limit. Those are the only two values that will ever be at in an on-off controller, or a high-low controller. So, and it's sort of doing the best job that it can. It just keeps monitoring whether this value is, above those limits or below them. But you can see here that particularly when the loading got to a point where it started to increase, the DO starts to drop off quite a bit before the ammonia actually gets to the point where it is already reacting. So it's a bit of a slow controller in that sense, that it waits till things kind of have already hit the effluent before it actually sees something in order to be able to make a change upstream. So you get sort of quite a drastic drop here, and of course the same thing the other way. So once the loading was dropping off, we could see here that we were actually over aerating for quite a while here, and the DO was starting to get really high before we finally got to that setting here, in which case it dropped down to the lower setting. So that's the way that one works, and it kind of works as it's supposed to. And just to continue to fill out our table here, we're looking at 13.5 tons, so a little less than doing the on-off DO control. And again, it really is kind of a bit of a slow controller in the sense it doesn't react really quickly. So there's periods of time where it's really over aerating and also under aerating as it's waiting to see the response in the effluent. So again, not really the type of system that might be the most optimal, but you can certainly model it and see how it goes. Okay, on to the last one. Cascade Ammonia Control. So basically this is, and I've done a couple of projects with this, it's actually a really fascinating process. This is actually using two controllers together. It's sort of the best of the PID DO control combined with the on-off ammonia control. So you actually have two controllers. You start with an ammonia controller that is on-off and it's looking at that effluent ammonia. But rather than setting or controlling the airflow directly, what it does is it actually controls the set point of a regular PID DO controller. And that controller is the one that it, adjusts the airflow in order to meet a certain set point. So in other words, when you have the ammonia start to get really high in your effluent, this thing is going to hit that limit and it's going to say, okay, it's time to go to a higher DO set point. So there's more air being applied. Goes to the higher DO set point, the PID controller then responds and makes the appropriate change to the airflow. Then you kind of get to the point where maybe the loading to the plant isn't so high, the ammonia starts to drop off. The controller says, okay, now we've hit our lower limit, where our effluent ammonia is certainly very low, it's down to 0.1 or what have you. Let's actually say we don't actually need as much air. So we're going to back that off, tell the PID controller that, you know, we can get away probably with 1 milligram per liter of oxygen because we certainly don't have a huge ammonia load at this point. So the controller acts appropriately and changes the airflow. So you got two of them acting sort of in series in order to be able to handle that kind of control. So let's pop over to that one. And we will run this very same simulation again. And in this case here, we can see we're starting out with, I'm going to control settings here. When there's a very low load, very low ammonia here in green, it's keeping the DO set point at 0.5. But as soon as it's kind of got above that band, and again, I made a relatively tight band, you see that the DO set point jumps up here to 2. And then this does its job, and not only is this being controlled, but this is the airflow, which is also being controlled in concert with that set point. You can see the DO is down here where it was supposed to be. Then the set point changed. The DO, then the controller, the PID controller, then came way up here that you can see it's turning up that airflow in order to meet that DO control. The effluent ammonia is obviously we're still spiking a little bit, but it's coming along here. And then when we get to a point when this ammonia is going to come back down, it's going to drop that down again. And I'll again just not to or speed things up a little bit here, I'll take a screenshot of what I had all the way through. So as the system responds back and forth, you can see that it takes the opportunity to not only turn down the airflow in the sense that it responds to a change in the load, but it also looks at a change in the effluent. So it even says that, you know, when there's nothing coming out in the effluent or it's doing its job, there's an opportunity to even back off the airflow a little bit more. So to fill out our table here, lastly, we can look here. We got sort of very similar type of effluent quality to the first two that we were doing, but we did it for much less money. So we're using less energy, and we got $57,500 or $720. So now, all of these numbers that you're seeing here in this table are completely specific to the hypothetical example that I've created with a hypothetical plant and a hypothetical influent. So. But as I was going through this week, it was a really kind of fun exercise to be able to sort of experiment around. This Cascade controller, you know, you've got quite a few settings in that controller that you can optimize. You know, what do you want that band to be in your effluent quality? Are you willing to, you know, let a bigger spike come through, or does it have to be really tight? At the same time, you know, what kind of DO settings are you willing to have in order to be able to try and meet that? And there's an optimization, I think, there in those 4 bounds, plus also the amount that of air that you'll be able to supply in order to hit those DO set points. So it's really kind of a fascinating little system, and the best part of it all is that you can use GPSX to model it and be able to understand how those things go together. So just a few conclusions here, as I've already run out of time, I see. Excuse me. GPSX certainly has a multitude of flexible controllers of various kinds that allow you to design and test and try out different control strategies and learn from the model about what works and what doesn't. Now, if you combine that information as we have here with the operating cost models that are in GPSX, you can really have that nice balance between effluent quality and cost. You can analyze the amount of energy that's being used, and you can analyze the amount of, the quality of the effluent, and be able to understand how much ammonia is coming out. And a lot of these controllers are relatively easy to set up in the sense there's only sort of 2 or 3 things that you need to do, but the PID control ones are a little more finicky in the sense that you have to do a bit of tuning as well. But that's all part of being able to do process control, is understanding how these things work, and optimizing those control loops, and trying to find out the best sampling time and the best DO set points and so on. And modeling is definitely a very useful tool in that respect.